Today we're going to explore two key physics concepts, free fall acceleration and terminal velocity, using something simple like a coffee filter. When objects fall under gravity alone, like this filter, a phenomenon they experience is what we call free fall acceleration. On Earth, that acceleration is always 9.8 meters per second squared, or g. That means every second an object falls, its speed increases by 9.8 meters per second, if nothing is affecting the falling acceleration. What to measure for the experiment includes F, d equals drag force, c equals drag coefficient, rho equals air density, g equals acceleration of gravity, m equals mass of coffee filter, a equals area of coffee filter, v equals velocity. The scale and measurements used in the calculations was the bookshelf, which was 1.168 meters. Time of drop, 4.86 seconds. Height of drop, 5.372 meters. The area of coffee filter, A equals pi r squared 0.99006 meters or 3.9 inches is the measured radius. A equals pi 0.09906. A equals 0.03082 meters squared. Mass of coffee filter, 0.004 kilograms. Air density equals 1.225 kilograms over meters cubed. The drag coefficient equals 1.0, g equals 9.8 meters per second squared. Now onto the video analysis of how we conducted the experiment. These are the two graphs depicting the position and velocity of the coffee filter as it was falling down. As seen in the video, this filter isn't falling very fast. Why is this? That's because air resistance is pushing up against it as it falls. This upward force is called drag. At the start of the fall, gravity succeeds in pulling the filter downward, and it starts to accelerate. But as the filter picks up speed, air resistance pushes harder and harder upward. Eventually, these two forces, gravity and air resistance, become perfectly balanced. When the forces balance out, the filter stops accelerating. It falls at a constant speed. This is termed as terminal velocity. In this project, terminal velocity is depicted through watching an object fall quickly at first, and then slowing down due to the air resistance. The predicted terminal velocity was calculated to be 1.11 meters per second, and the actual observed terminal velocity for our experiment was 1.44 meters. Lastly, due to the air resistance, it slowed the acceleration of the coffee filter and didn't fall long enough for drag to fully balance gravity, resulting in not reaching terminal velocity, which made the observed terminal velocity lower. Even though the terminal velocity wasn't fully reached, our experiment still confirms physics predictions and depicts a real example of free fall acceleration.